In the previous videos, we introduced some branches of philosophy of science that are important for you to understand, including ontology, epistemology, axiology, and logic. In particular, within logic, we presented three different types of inference and how they differ in forms and in their targets. Historically, particularly deductive and inductive inferential methods have been pitted at odds against one another with respect to their value in science. However, it's a matter of fact that at various stages in different scientific disciplines and at different times and in different contexts, scientists find themselves practicing all three of these kinds of inference. So therefore, it's valuable to think about scientific inference in general and the scientific method in some sort of holistic manner. The following figure tries to convey that kind of holism, that kind of interleaving, that essential relation between all of the different aspects of scientific inference that we've discussed. It's broken down into three key areas, and this actually relates to the way the philosopher Roy Bhaskar broke up the world epistemologically. So we have the empirical world, which is in the grey box, and this is where we actually make observations. This is where our data actually comes from. It is the experiences we have, the things we measure. Then we have the actual world. This is where our concepts of phenomena and the events that occur actually happen, the generalizations that we make from the data. And then we have what he referred to as the real world, but probably better referred to as the causal world for those who within their ontology include things such as causal powers and mechanisms to explain things that they've observed. Now, how are these all tied together? Well, in the empirical world, we can start with some kind of scientific theory, and that scientific theory entails some kind of model. We can take that model and we can operationalize it into something that we can actually implement within a piece of research, within a study. We can make observations, and these observations form the data that we are actually interested in. Now, with our theory, we can make predictions. We can generate a model, we can operationalize it as a study, and we can predict what kinds of observations and therefore what kind of data would be consistent with our theory. So deduction is the process of taking our theory as a premise, making predictions, and then testing them, all within the empirical world. Or, from our data, we might inductively make generalizations about our theory if we want to use that inductive approach of inference. But we can also use our empirical observations to generate generalizations about phenomena and events. So we might observe, for example, using the white swans again, that every swan we've seen so far is white. And therefore we may say that it is a particular generalizable phenomena that all swans happen to be white. That is just the phenomena. Swans are white. But from that generalization, we might actually want to try and explain that phenomena. It's not enough necessarily to just say, yep, all swans are white, that's fine. We might want to explain why that's the case. And this is where abduction comes into it. So from abduction, we might come up with explanations for the kinds of causal powers or mechanisms that might exist to explain those phenomena and events. We might also think about how different causal explanations explain the data that we've observed and used to induct those phenomena and events. And finally, that combination of phenomena and generalizable phenomena and events and causal powers or mechanisms, if we indeed believe they're included in our ontology, can be used to create explanations and theories that then re-enter that empirical testing process. So whilst the rubber meets the road and our theories have to be tested in the empirical world, we create ideas about phenomena and events, we create concepts referring to them, we create concepts referring to possible causal powers that explain them, and then we generate theories that we then take out into the real world and test. We either test it deductively and try to falsify our theory, or we inductively test it and we see whether or not we can obtain data that might confirm our theory. But all in all, depending upon the stage of research we're at, whether we're building theories, whether we're trying to determine whether there are constant generalizable phenomena and events that we can induce from data that we observe, or whether we are at the stage where we have a robust theory that makes clear predictions that we can then go out and test and attempt to falsify. All kinds of inference do have their key place within a broad holistic scientific method. It's important for you to think, when you're conducting your own research, what sort of stage you're actually at. Is the research that you're conducting based upon some established theory that makes clear predictions about what you should go out and observe? Therefore, you can set up a study to try and test that. The study should be aimed at trying to falsify that, to see whether or not you do actually observe them. And if you don't, you might conclude that the theory is false, or at least it's in question. Or, if you observe data that confirms the theory, you might inductively generalise that, well, the theory is perhaps true. In some fields, though, we don't yet have strong enough theories to make these sorts of predictions. So instead, we make our observations absent the theory, and we try to generalise about what kinds of phenomena and events actually exist. We might be in a stage of research where we do have regularly occurring generalisable phenomena, and what we're actually trying to do is build explanations and build theories about the potential causal powers that might explain them. So think about this when you're designing your research. What kind of research is it? What's it aimed at? What are you trying to do? What kinds of inference are going to be most appropriate for what you're trying to do?